Thanks for Michelle. And I'm Yuan Liu from Chinese Academy of Sciences, and this is joint work with the University of Amsterdam. So we all know with the development of the deep learning, the effective neural ranking models are popular across both academia or industry. However, beyond the effectiveness, the neural ranking model, do you want to take a photo? Thank you. So beyond the effectiveness, the neural ranking models are not robust. They are likely to inherit the vulnerabilities of general neural ranking models. Let's see, if given a low-rank document and you just need to add some very slight perturbation on it, the ranking of it would change so much. So these vulnerabilities are potential to be exploited by the search engine optimization. So that's why we studied the virtual ranking attack. First, we want to evaluate the vulnerability of neural ranking models. And then we want to use faults identified by our attack method as a surrogate evaluation and help the defenders to strengthen our model. So typically, the virtual ranking attack is to promote target documents in rankings with respect to a query. So there could be many choices of the perturbation, maybe the word level, the word substitution, or sentence level, or something. So as you can see, the existing work usually focuses on single granular perturbations, such as word level perturbations. You just change the word to the synonymous, and about phrase level perturbation, you just with a phrase substitution or even sentence level perturbation. All this work focuses on one type of the perturbations and to perform attacks. So here's the two steps of the existing method. So first, they identify the wordable positions in their target document, and they predetermine a type of perturbations, and then they generate the specific perturbations with a single tab on the document. However, we find that there's something wrong, because as you can see, the wordable perturbation, maybe we can name it to the wordability distribution of our target document. Sometimes they are a single point, so they are appropriate for some fine-grained perturbation, like just change some words or a phrase on it. But other times they are continuous span. So it's appropriate for us to add a sentence on it. It can make a continuous optimization method. So as you can see, according to the existing method, these two steps are holding each other back if you choose the wrong perturbation to the wrong document. So we propose multi-granular ranking attacks, which allowing for flexible selection across these three types of perturbations. And they can finally generate richer and more diverse forms of our adversarial examples. However, generates adversarial examples by multi-granular is not true, because we were facing a computational exploration. First, there are many positions for us to choose, and then we should determine which exactly the granularity at each positions. And finally, we will specifically generate the perturbation content at the selected position. So we model this attack process as a sequential decision-making process. So at each step, we find a position and generate a specific adversarial perturbation on it. And we will see what's going on. The ranking change to which position. And based on the situation, we generate the next perturbation one by one. So we use reinforcement learning to model the whole process, which contains of our environment, is our ranking model that gives the signal of the ranking improvements. And we use a larger model to make sure that our perturbation generated is natural. And they put the rewards into our agent that generates the perturbations. We have two agents collaborated together. So the first sub-agent determine where to attack. They identifying the multi-granular vulnerabilities in the document. And finally, feed to the meta-agents. The meta-agent determine how to attack. Yet, based on the generated positions, they generating and organize this across many types of perturbations into a final perturbation sequence. And then we got the final adversarial examples. So I think this two agents can collaborate very well, and so then can generate the powerful example. So as for the reward, for each attack steps, if our attack is succeed, if the ranking is improved, so we take the ranking improvement with a discount and combine to the naturalist evaluation with the larger model together as our the final reward. However, if the ranking is defined, we give the model a penalize, and then we go back again. As for the baselines, we compared our method with some single granular method. Yeah, that's word level attack, phrase level, or sentence level attack. And we also designed some model variants of our method, such as just like a single type of perturbations, and incorporates all these type of perturbations, make sure the three type of perturbations all integrated in our document. Also, we drop our reinforcement learning process, or just use a gradient method to choose variable spans and to perform attack. And as for the target model, we use to attack the bird crossing encoder, prop model pre-trained tailored for ranking tasks, and a larger language model also. So we evaluate our attack performance as how many documents the ranking are improved, and how many ranks they are improved, and how many the percentage of the documents they are both into the top K, which we mainly focus. And on the other side, we focus on the naturalness of the performance, that our generated adversarial example should be past the grammar checker. Yeah, it should be similar enough according to the original example. Yeah, we have to do some specificity detection and with the perplexity, or do some human evaluation. So, as for the experiments, we can see that compared to the basic single granularity method, our multi-granularity attacks achieve the best performance. So, the single granularity is not sufficient to fully use the diverse workability distributions of our document, reflecting the neural models, and the serving between the perturbations of different granularity generates straightened adversarial examples for us. And on the other hand, when we compare our method to our variance, we can find that the sequential decision-making, adding the perturbations enables more effective exploration according to these perturbations. And our method of relativations is very flexibly to organize the multi-granular perturbations in generating high quality examples. And so there is a case study of our method generated different levels of perturbations in a document and making the progress of the ranking. Okay. So I think that's all, and you can refer to our GitHub for the more details of our experiments. And there is also a survey about robustness on tag information retrieval in this field. Okay, so thank you.